about the optimal quantization in this clustering to the simulation with the McKean Vlasov equation. First, I will introduce the concept behind the optimal quantization, then the McKean Vlasov equation. For the optimal quantization, I will address three questions: what, how, and why. What is optimal quantization? First, what is quantization? The quantization method provides a discrete representation. Here, this mu hat x, our probability measure. When I talk about the discrete, this means the mu hat x somehow a weighted sum of a Dirac measure on some points here, x1 up to sk. We call these points the quantizer. The number of the points k is called the quantization level. Here in this discrete representation, the weight is computed by the mass of mu on some Voronoi cell. So what is optimal? If a quantizer x star satisfies that the Wasserstein-2 distance between this discrete representation and the original measure equals the infimum of the Wasserstein-2 distance between mu and nu for every nu having it has a support of at most k points. If this holds true, then x star is called an optimal quantizer. Here on the left-hand side, I show an optimal quantization for the normal distribution in dimension 2, where the blue points represent the quantizer and the red colors represent the weight. On the right-hand side, this is not optimal. We can easily say the difference between optimal and not optimal.
Can I ask something?
Yes.
So here, are you fixing what k is? Somebody gives you k, because the picture will change. Like if k was 1, I guess you would just have to put something on the mean of your Gaussian.
Yes.
Yeah?
Yes.
Okay.
Yes.
So okay.
K is perfect.
Sorry, k is
Prefixed.
prefixed. Okay, thank you.
Now the relation between optimal quantization and k-means clustering. K-means clustering, I think everyone knows here. For an unlabeled sample, involves finding the cluster centers that minimize a cost function here. For example, this is our data set if k equals to 3. What we want to find are green points here, which represents 3 clusters. And what is the relation between optimal quantization and k-means clustering? Is if we, it's quite straightforward. If we find an empirical measure over the data, then the optimal cluster center in the k-means clustering sense is equivalent to the optimal quantizer that I presented in the previous page in the optimal quantization sense. Now, the second question, how to find an optimal quantizer? For example, we can use Loy's algorithm because the optimal quantizer is stationary in the sense that the expectation of x, which is a random variable having the distribution mu, given the the x hat x star, which is the projection of this random variable onto the quantizer. This conditional expectation still equals x hat x star. The projection function is defined by, okay, maybe we'll take a look at the picture. The projection function sends on point here to the nearest point in the quantizer. The Loy's algorithm comes from this idea. What we compute is essentially the same conditional expectation. We compute this iteration until the quantizer becomes stable. Of course, Loy's algorithm is just one method. We can also consider other methods, for example, zero finding or the gradient of the distortion function to find an optimal quantizer. Now, the third question, why? Why do we choose optimal quantization method? The first reason is that the optimal quantization provides a deterministic discrete representation for mu. Unlike the Monte Carlo method, the optimal quantizer X star and this discrete representation are deterministic. The second reason is here I write smaller size for the reason that if we want to achieve the same accuracy level, we need less point in the quantizer than in the Monte Carlo method. This is equivalent to say if we consider the same level here, the same number of points in the quantizer and the same number of RID random variables in the Monte Carlo method. If we evaluate the error by using the Wasserstein distance, then the optimal quantization error is almost surely less than the error of Monte Carlo method. Here on the right-hand side, I show optimal quantization for the standard normal distribution by using only 5 points. It looks not bad, right? Only 5 points. I don't want to challenge Monte Carlo method. I teach Monte Carlo method in my university, but imagine that if we want to use Monte Carlo method with only 5 RID random variables, it would not be so nice like this. The third reason why we choose optimal quantization is the optimal quantization error is controllable. This error can be upper bounded by a universal constant and some constant depending on mu times k power minus 1 over d. Of course, using quantization method comes with some challenge. The first challenge is the curse of dimensionality. This term in Zador's theorem. The second challenge is the computational time required to find optimal quantizer. It may be costly, especially in high dimensional setting. Now I will introduce the McKean Vlasov equation. The McKean Vlasov equation that we consider in this talk is defined by this equation, where the coefficient function depend B and sigma depend not only on the position of xt, but also its log, its probability distribution. Here, the mu t denotes the probability distribution of xt. One classical example of the dependence on mu is what we call the Vlasov case. This coefficient function bx mu is the integral of another function with respect to mu. The assumptions. First, we need to assume that x0 is known and computable. It's in LP. We assume that the coefficient functions b and sigma are Lipschitz continuous in x and in mu with respect to the Wasserstein distance. And we assume that b and sigma are computable for a discrete probability measure. For example, in the Vlasov case, if we consider a discrete probability measure like this, a weighted sum of Dirac, if we consider measure like this, then the integral becomes a weighted sum. These conditions are classical conditions for the existence and the strong uniqueness of the solution to the McKean Vlasov equation. Now the numerical part. We want to simulate the solution to the McKean Vlasov equation. So we start with the McKean Vlasov equation. First, we can write the Euler's game. It's kind of time discretization that we saw yesterday, in fact. Unlike the Euler scheme for the standard diffusion process, here, this Euler scheme, I call it a theoretical Euler scheme because we cannot directly simulate it because of this term, mu bar Tm. To simulate the mu bar Tm, we need somehow additional space discretization to discretely represent each law to simulate the random variable of time Tm plus 1. How to do this? Here I show two methods for the space discretization. The first one is particle method, which is inspired by the publication of Kell's property of the McKean Vlasov equation. The idea is we simulate n particles, and this mu bar Tm is approximated by empirical measure over the particles. The second method that I will present today is, of course, by using the quantization method. As before, we will consider a quantizer, and this mu bar Tm will be approximated by the weighted sum over the quantizer. In this page, I will show the idea behind the particle method and the quantization method. On the left-hand side, the particle method, it looks like Monte Carlo, somehow like Monte Carlo, except in the McKean Vlasov setting, the particles are not independent of each other. On the right-hand side, here we show the idea of the quantization method, and we will approximate this law probability measure by using the quantizers, the right point here, and the weight, the green line here. Now I will briefly present the particle method, which is which has been well studied in the literature, also well studied by professors here in Edinburgh, I think. We start from the Euler scheme. Okay, the particle method is defined by this equation. We consider a particle system at time 0. Particles are IID random variable having the same distribution as x0 from time Tm to time Tm plus 1. Here in the major argument, instead of putting mu bar Tm, we will consider this empirical measure over the particles. For the particle method, we can compute upper bound of the convergence rate. Here, the Wasserstein distance between this empirical measure and the original measure in the Euler scheme can be upper bounded by times n power minus 1 over d. Of course, a small remark here is the discrete measure, the empirical measure over the particles is random. So when we need to evaluate the error of this method, we need to somehow take the expectation of the Wasserstein distance between these two. Now, the quantization-based scheme. As before, we start with Euler scheme. The idea of the quantization-based scheme is here. At each time Tm, we will pick quantizers, the right point here. And at this quantization step as a spatial discretization for computing the random variable of time Tm plus 1. Which means here in the major argument of the coefficient, instead of consider the mu bar Tm, we will put a weighted sum of Dirac into the coefficient functions to compute the time Tm plus 1. Until now, you may ask, it's not very clear how to simulate this mu hat Tm, this quantized measure, because it depends somehow the law of the x tilde Tm. The answer is, to simulate this mu hat Tm, we can use either the recursive quantization method in the Vlasov setting or a hybrid particle quantization method. I will give more details later. First, the recursive quantization for the Vlasov setting. Recall that when we call an equation a Vlasov equation, it means that the dependence on mu is somehow an integral of a function with respect to mu. And the idea of quantization-based scheme is for every time every time step, we consider a quantized measure, mu hat Tm, which is a weighted sum of Dirac measure of the quantizer. Then in the Vlasov setting, we can rewrite the quantization-based scheme. Here, the integral becomes a weighted sum. It is quite straightforward, I think. First, we will consider a simple case. We fix the quantizer. Even it is not optimal, we just fix some quantizer. Pick some points in the space. Once we fix the quantizer, we only need to compute the weight Pm here to obtain this quantized measure. So now the question becomes, okay, we fix the quantizer. Now the question becomes how to compute the weight in this quantized measure. Here, this is the idea, the recursive quantization. At time 0, E0 can be directly obtained because we know x0. And the reason why we call this method recursive, because from time Tm to time Tm plus 1, given the weight of time Tm, what we want to compute is this transition probability, Ij, which is the conditional probability of the x hat Tm equals the jth one in the quantizer, given the x hat Tm equals the ith one in the quantizer. If we can compute this transition probability, then we can compute the weight of the m plus 1, time m plus 1. Essentially, what we do here in this history, what we do is just compute a Markov chain of the weight at each time. Okay, now the question becomes how to compute the transition probability. It is quite straightforward. Recall that the quantization-based scheme can be written like this. We know that here the random variable z is follows a normal distribution, standard normal distribution. So given the value of x hat and Pm, we know it's very easy. The x tilde Tm plus 1 follows some normal distribution, depends on the mean, which is this part, and the variance matrix depends this part. So the transition probability pi ij equals the probability, the conditional probability of this x tilde Tm plus 1, taking value in a jth Voronoi cell, given the value of x hat Tm. As we know exactly what is the conditional distribution of x tilde Tm plus 1, this is equivalent to compute a probability of some random variable z tilde taking value in the same Voronoi cell, where this random variable has the same distribution here, right here, gamma. In this history, the computational performance depends on, of course, the simulation of an integral over a Voronoi cell. Voronoi cell in dimension 2 looks like this. In dimension 2. Which is, in fact, this integral over Voronoi cell is here. I want to compute the probability of some random variable having normal distribution taking value Voronoi cell. And this computation is very fast and well performed in dimension 1, as Voronoi cell in dimension 1 are only segments. Now, the last question. Until now, we just discussed for a fixed quantizer. The last question will be, is this possible to compute an optimal quantizer in this history? Of course, the answer is yes. Recall that just in the previous page, if we know the value of x at Tm and Pm, we know the random variable of time tn plus 1 follows some normal distribution. And recall the Lois algorithm for searching an optimal quantizer for a probability measure is essentially compute this iteration. So given the value of x hat tm and pm, we only need to set the mu here equals the random equals to the normal distribution here in this Lois iteration to compute an optimal quantizer for the time tm plus 1. It's easy. But the computational performance still depends on the simulation of the integral over one cell. It's here. It's the integral over one cell in this part. Now I will present the hybrid scheme. First, recall the relation between the optimal quantization and the k-means clustering is essentially we quantize the empirical measure over the data. So the hybrid particle quantization schemes shares the same idea. We quantize the particle system. We consider the particle system, the particles as some data, and we quantize the particle system. Here, we pick a quantizer of the empirical measure over the particles. And as before, in the major argument of the coefficient functions, we just plug in this quantized measure of the empirical measure. Maybe I'll show the picture here to show the idea of the hybrid particle quantization method. The idea is at each time, from the particles, we add k-means clustering step, and we compute the particles of the next step from the cluster center. Here, two remarks compared with the particle method. Why we use the hybrid particle quantization method is that we only need to store the quantizer, the green points, and its weight represented by the color to obtain a discrete representation of the major mu bar Tm. Another remark is that in many applications, in the research of the McKean Vlasov equation, we focus on particle system and then particle system. And the McKean Vlasov equation is only the limit equation when the number of the particles tends to infinity. If we consider the particles as a data set, this additional k-means clustering step is heuristic for modeling, given that k-means is commonly used for identifying features and natural classification in supervised learning. For example, the McKean Vlasov equation is used to model the opening dynamics. We can somehow consider the cluster center as some opening leader, something like that. Now I will show two simulation examples. The first example is one-dimensional Berger's equation, which can be found in the paper Bossi and Dalai 1997. We pick this example because we can compute the true relative distribution function. So we can compare the true function with the simulated one. In this example, we will compare the particle method and the recursive quantization scheme. On the right-hand side, the first figure is a particle method, and the second is the recursive quantization. Both methods work well. But if we want to compare more in details, here for the particle method, this is a random algorithm. So we need to rerun independently and identically several times for each value of n, the number of particles. And the recursive quantization method, as I mentioned before, is deterministic. We only need to run one time, and that's it. And if we compare the error, we can notice that if we take the same number in the particles and the same number in the quantizers, the error of the recursive quantization method is less than that of particle method. This is consistent with the comparison between the optimal quantization and the Monte Carlo methods. The next example is a three-dimensional neural network. This is not a neural network in machine learning. This is a real neural network. In this example, we will simulate the first two marginal distribution and compare the particle method and hybrid scheme. Here is a simulation result. On the left-hand side is the simulation result by the particle system, and this is a hybrid scheme, where the blue points are the quantizer and the red color represents the weight. But for this example, we don't have the true solution, so we cannot compute the error as before. Summary and outlook. A brief summary of these three methods: deterministic or random, the particle method and the hybrid scheme are random, and the recursive quantization scheme is deterministic. Computational time in dimension 1, the particle method and recursive quantization are fast because essentially we compute a Markov chain in each method, and the hybrid scheme is slow because we add a k-means clustering step at each time step. The computation time in dimension greater than 2, here the recursive quantization becomes slow due to the integral, the computing time of the integral of a density function over a Voronoi cell. And for the obtained data size, the quantization-based scheme have smaller data size. This is consistent with the fact that the quantization or k-means clustering is used for data compression in applications. Comments and outlook. The recursive quantization scheme, and of course the process of integrating Loi's algorithm into this scheme, requires rapid computation of numerical integration over a Voronoi cell. So I repeat, the Voronoi cell looks like this. Version 2. This becomes numerically costly in high-dimensional setting. For example, if we use a package like QHAL, it's become really slow when dimension equals it's greater than 10, something like that. Hence, if we can develop a faster computation algorithm for such numerical integration over Voronoi cell, this will be very useful for applying the recursive quantization scheme in the future. The next comment is on the error of the quantization-based scheme. Here, the current upper bound, we can just write a current upper bound on the simulation error of the quantization-based scheme like this. This bound contains an accumulation of quantization errors. Here, quantization errors. So accumulation means the sum over the time discretization. However, this divergence in M was not observed in simulation examples, even with a large value of M. Then investigating another error bound and determining conditions for the convergence will be another direction for future research for the quantization-based. I think I will stop here. Thank you for your attention.